myself, Dr. Ashok Babu, working as professor and head of the department, ECE. In this video, I am going to discuss about the electric flux density, Gauss law, and some of the applications of Gauss law. First, we'll define what is electric flux density. So, to define electric flux density, now let us assume some vector field D, where D is the electric flux density, and which can be defined as D is equal to, it is some epsilon naught into E, where epsilon naught is the permittivity of free space, E is the electric field intensity. So, by the definition of electric fields, electric field charge distribution, we can define the electric flux psi in terms of electric flux density D, where psi is the electric flux, D is the electric flux density. So, psi can be defined as, it is a surface integral of D into ds. Surface integral of D into ds will give the electric flux. So, here electric flux will start from positive charge and it will end at the negative charge. Therefore, it can be measured in terms of coulombs. Electric flux can be measured in terms of coulombs. So, here, therefore, the vector field or electric flux density D is called the electric flux density and is measured in coulombs per meter square. It is measured in coulombs per meter square. The electric flux density is also known as electric displacement. The electric flux density is also known as the electric displacement. Already we have derived some equations in previous videos. That is, we know that the electric field intensity for surface charge. The electric field intensity for surface charge is given by, for surface charge of infinite sheet, is given by electric field intensity E is equal to, electric field intensity E is equal to, we have rho s by 2 epsilon naught into an, where an is a unit vector, rho s is a surface charge density. Rho s is a surface charge density. So, according to the definition of electric flux density, here we can define the D, electric flux density, D is equal to, we can define epsilon naught into E. So, from this equation, so here we can write, already you have E is equal to, it is rho s by 2 epsilon naught into an. So, here it is E into epsilon naught is equal to, it is rho s by 2 into an. So, here E into epsilon naught is known as the electric flux density D. Therefore, D is equal to, we have rho s by 2 into an. So, which is an expression for electric flux density of a infinite sheet of charge. Similarly, we know that the volume charge distribution, D is equal to, is a volume integral rho v dv by 4 pi r square into r. Or in another way, we can express it as D is equal to volume integral q dq. dq is a elemental charge. dq by, or it can be expressed as D is equal to volume integral, it is dq by 4 pi r square into r, where dq is the elemental charge. dq is nothing but rho v into dv. Therefore, here the electric flux density D is equal to, it is volume integral rho v dv by 4 pi r square into r. So, actually it is having the expression E is equal to, electric field intensity E is equal to, it is volume integral, it is q by 4 pi epsilon naught r square into ar, where q is the, or we can express it as dq. dq is the elemental charge. Therefore, if you multiply the E and epsilon naught, E into epsilon naught is equal to, it is volume integral, it is rho v dv, or in place of rho v dv, we can write dq by 4 pi r square into ar, where ar is the unit vector along the r direction. So, here if you observe the equations 3 and 4, D is a function of charge density. And position only. It is independent of the medium present. So, D is independent of medium present and D depends upon the, or D is a function of charge and position only. Now, here we can define the electric flux density in different ways. So, first one is, so electric flux density, it is a measure of strength. It is a measure of strength of an electric field generated by a free electric charge, corresponding to the number of electric lines of force passing through a given area. Let us assume some given area. in that given area, it is a measure of strength of an electric field generated by a free electric charge corresponding to the number of electric lines of force passing through a given area. So in a simple manner, we can define the electric flux density in another way. It is equivalent to the electric field strength. It is equivalent to the electric field strength multiplied by the permittivity of the material. Multiplied by the permittivity of the material through which the electric field extends. Or in a simple manner, D is equal to, it is epsilon naught E. D is equal to epsilon naught E. So it is equal to the electric field strength E, multiplied by the permittivity of the material. We can call it as a simply electric flux density. Electric flux density. So here we'll see some small example for electric flux density. So here determine electric flux density D at point 4, 0, 3. If there is a point charge minus 5 pi millicoulombs, which is located at 4, 0, 0, and a line charge, it is 3 pi millicoulombs per meter along the y-axis. Here we need to find out the electric field intensity due to the line charge and due to the point charge. So here we need to find out the electric flux density due to the point charge and electric flux density due to the line charge. Continuous charge distributions like line charge. So here the total electric flux density D is equal to dq plus dl, where dq is the electric flux density due to the point charge, dl is the electric flux density due to the line charge. So here we'll find out the electric flux density due to the point charge separately and electric flux density due to the line charge separately, and we will add so that we can get the total electric flux density. Therefore, first we will find out the electric flux density due to the point charge. So electric flux density due to the point charge dq is equal to, we can write epsilon naught E, which is equal to, it is dq is equal to q by 4 pi r square into ar. Q by 4 pi r square into ar. Actually, we have the formula electric field intensity E is equal to, we have the formula electric field intensity E is equal to q by 4 pi epsilon naught r square into ar, where ar is a unit vector, r square is a magnitude, and again it is E is equal to, we can write q by 4 pi epsilon naught, where ar is the unit vector, therefore it can be expressed as r by mod r cube. So where r is a vector, it is a magnitude of the vector. Therefore, so here we need to find out the electric flux density. Therefore, electric flux density D is equal to, it is q by 4 pi into r by mod r cube, mod r cube. Or in place of r, we can write the distance vector r minus r dash, where r minus r dash is the distance vector between the 2 points. Modulus of r minus r cube is the magnitude of the vector. For the formula can be, it is dq is equal to epsilon naught into E, which is equal to q by 4 pi r square into r. Then it is q into r minus r dash by 4 pi into r minus r dash whole cube. First, we will find out the distance between the 2 points. So here r is the 4, 0, 3 and r dash is the 4, 0, 0. So if you find out the distance between these two, so we have 0, 0, 3 only. We have only z component. Then the formula for electric flux density dq is equal to, it is q, in place of q, the point charges, it is minus 5 pi millicoulombs, minus 5 pi into 10 power minus 3 into r minus r dash, distance vector 0, 0, 3 by 4 pi into modulus of r cube. We need to find out the modulus of r cube. It is modulus of 0, 0, 3 whole cube. So if you expand that expression, we have the minus 0.138 Az millicoulombs per meter square. Because we have only z component, the total electric flux density is along the z axis only. Next, we will find out the electric flux density due to the line charge. To find out the electric flux density due to the line charge, here we have the formula electric flux density of a line charge is equal to, we have rho L by 2 pi epsilon naught rho into a rho. We have E is equal to rho L by 2 pi epsilon naught rho into a rho. If we multiply epsilon naught and E, which is D, D is equal to E into epsilon naught which is nothing but rho L by 2 pi rho into a rho, where a rho is the unit vector along the rho direction. So first we will find out the a rho. So where a rho is equal to r by mod r, distance by modulus of the distance, where the 2 points are 4, 0, 3. The first point is 4, 0, 3, and the second point is origin, which is origin 0, 0, 0. Therefore, the distance vector is 4, 0, 3. Here we have x component and z component, and the modulus of the distance is, it is root of 4 square plus 3 square. It will give us the 4 square 16 plus 9, root of 25. So out of the root it is 5 only. 4. And the rho is the distance, magnitude of the distance. Rho is equal to 5. So if you substitute all these values in this equation, in the equation of rho L by 2 pi rho into a rho, then we have, it is rho L is 3 pi, already is given as 3 pi by 2 pi into rho. 2 pi into rho is 25. Rho is nothing but 25. So it is modulus into, so here it is the vector difference, the distance vector is 4ax plus 3az. 4ax plus 3az. So if you simplify the equation, the expression is like this. So if you add the both electric flux density of point charge and electric flux density of line charge, the total answer will be like this in micro coulombs per meter square. So this is about the electric flux density and a small example on the electric flux density. Now we will discuss the Gauss law. So what is the Gauss law? So Gauss law is one of the basic laws in electrostatics, so which constitute the fundamental laws of electromagnetism. So Gauss law states that, the total electric flux psi, through any closed surface is equal to the total charge enclosed by that surface. So let us assume a closed surface. If we assume a closed surface, then according to the Gauss law, the electric flux psi through any closed surface is equal to the total charge enclosed by the surface. So the total flux is a psi. Psi in any closed surface is equal to the charge enclosed in that closed surface. Psi is equal to Q enclosed is the Gauss law. According to Gauss law, we have psi is equal to Q enclosed. But already we have defined the psi flux using the electric flux density. Using the electric flux density, we can define the flux. So therefore, psi is equal to, it is surface integral d psi. Psi is equal to surface integral d psi, which is equal to, so according to the flux density, it is surface integral d into ds. According to electric flux density, we can define the electric flux as psi is equal to, it is surface integral d into ds. Surface integral d into ds. Next, we know that the total charge enclosed in volume, over a volume, the total charge enclosed is Q is equal to, it is a volume integral rho v dv. If it is a surface, it is surface integral rho s into ds. If it is a line, it is line integral rho l into dx. Depending upon the surface, we can define the charge here. So Q is equal to, it is a volume integral rho v dv. And we can express that Q, we can equate the charge. We can equate the charge as Q is equal to, already we can define the charge Q is equal to, the charge Q is equal to, it is surface integral d into ds, because, so here according to the Gauss law, we can write the total flux is equal to charge enclosed. Therefore, psi is equal to Q is equal to, psi is equal to Q is equal to, we can write surface integral d into ds, which is equal to the charge in a volume is equal to volume integral rho v dv. Volume integral rho v dv. Next, we will recall the divergence theorem. According to the divergence theorem, it is some surface integral a into ds, where a is some vector. It is surface integral a into ds is equal to volume integral del dot a into dv. It means if you apply a divergence theorem to the vector, if you apply a divergence theorem to the vector in surface, then the surface integral may convert to the volume integral. If you apply a divergence theorem will convert the surface integral to volume integral here. So here a surface integral of a into ds will becomes volume integral of del dot a into dv. Now we will apply the same divergence theorem to the second term of equation 3. Second term of the equation 3. So here second term of equation 3 is, it is surface integral d into ds. surface integral, closed surface integral d into ds. So if you apply divergence theorem to the middle part of the equation 3, then it becomes, it is volume integral del dot d into dv. Volume integral del dot d into dv. It becomes, surface integral will becomes the volume integral. It is surface integral d into ds equal to volume integral del dot d into dv. So it is the equation 4. Next, if you compare the equations equation 3 and equation 4. If you compare the equation 3 and equation 4, equation 3 is Q is equal to volume integral rho v dv. So here it is volume integral del dot d into dv. If you compare the two volume integrals, so here we can write rho v is equal to del dot d. Rho v is equal to del dot d. So let us assume this equation 5. So which is known as the Maxwell first equation. Maxwell equation for electrostatics. Maxwell first equation for electrostatics, which is del dot d is equal to rho v. It can also be expressed as, we know that d is equal to epsilon naught d, epsilon naught e, in place of d, e into epsilon naught, which is rho v. Therefore, del dot e is equal to, we can write rho v by epsilon naught. So it is another form of Maxwell first equation for electrostatics. We can express it as del dot d is equal to rho v, or we can express it as del dot e is equal to rho v by epsilon naught. Next, the above equation states that the Maxwell equation states that the volume charge density rho v is equal to, rho v is same as the divergence of the electric flux density. So we can observe the some points from the Maxwell, from the Gauss law. The first point is equation 3 and equation 5. So equation 5 is rho v is equal to del dot d. Equation 3 is Q is equal to, it is surface integral d into ds equal to volume integral rho v dv. Equations 3 and 5 are basically stating the Gauss law in different ways. So equation 3 is the integral form, whereas equation 5 is the differential form, or which is also known as a point form. Or equation 3 is known as the Maxwell equation in integral form. Equation 5 is known as Maxwell equation in differential form. Next, second point. So we can observe that the Gauss law is an alternative statement of Coulomb's law. So proper application of divergence theorem to the Coulomb's law will result in Gauss law. Proper application of divergence theorem to the Coulomb's law will result in Gauss law. So these are the two important points we need to observe from the Gauss law. Now we'll see some applications of Gauss law. So before applying a Gauss law to any surface, we need to follow some rules and regulations. So here, what is the rule? To apply a Gauss law to any surface, we need to check that, so whether there is some uniform charge distribution is there or not. If there is some uniform charge distribution, then only we can apply the Gauss law. Our Gauss law is applicable to the uniform charge distribution only, whereas Coulomb's law can apply to the uniform and non-uniform charge distributions. But Gauss law is applicable to the only symmetrical charge distribution only. So first we need to check that symmetrical charge distribution. If symmetrical charge distribution exists, then we need to construct a mathematical circle. We need to construct a mathematical closed surface, which is also known as a Gaussian surface. Next, we need to check that the surface is chosen such that the electric flux density D should be normal to the surface. Here the D may be normal to the surface, or D may be tangential to the Gaussian surface. When D is normal to the surface, then we can write D into ds equal to dds. We can just simply multiply the d and ds. Next, if D is tangential to the surface, then d dot ds equal to 0. Then we cannot apply the Gauss law to the particular Gaussian surface. Okay, these are the rules and regulations we need to follow when we are applying the Gauss law to any surface. So first one is, we need to check that whether there is some uniform charge distribution. If uniform charge distribution is there, then we need to construct a mathematical closed surface, which is also known as a Gaussian surface. Then the third one, we need to check that the electric flux density D should be normal to the Gaussian surface. When electric flux density D is normal to the surface, then only we can apply the Gauss law. If electric flux density D is tangential to the surface, then directly D dot ds should be equal to 0. Then we cannot apply the Gauss law to that particular surface. Next, so first application is a point charge. Here we can apply Gauss law to point charge, line charge, surface charge, and volume charge. So here as point charge is a constant one, and whereas a line continuous charge distributions like line charge, volume charge, and surface charges. So we can apply the Gauss law to all the 4 charges. So first we'll check the point charge. So let us assume a point charge which is located at the origin. Let us assume a point charge which is located at the origin Q. That Q is a point charge which is at the center of rectangular coordinate system. So we need to apply the Gauss law. To apply Gauss law, first of all, we need to check that whether there is uniform charge distribution is there or not. We let us assume some uniform charge distribution. When there is some uniform charge distribution, then second step is we need to construct a Gaussian circle or mathematical circle. So construct a Gaussian circle or mathematical circle. So here the circle is Gaussian circle or mathematical circle. Then third one, we need to check that D is normal to the surface or tangential to the surface. Here D is normal to the surface at any point on a circle. So when D is normal to the surface, then we can apply a Gauss law. Next, since D is normal to the surface on a circle, we can write D is equal to dr into AR, where dr is the electric flux density in R direction, AR is a unit vector along the R direction. Apply a Gauss law to the Gaussian surface or Gaussian circle. So here Gauss law is the total flux in any closed surface psi is equal to the charge enclosed in that surface. Then according to the Gauss law, Q is equal to the total charge Q is equal to surface integral D into ds, which is equal to where D is nothing but dr into AR. In place of D, you substitute dr into AR, where AR is a unit vector. Therefore, it becomes dr into surface integral 1 into ds. Surface integral 1 into ds. So here the surface integral ds is nothing but, so here the surface integral, the surface area of a circle, the surface area of a circle is nothing but 4 pi r square, where r is the radius of a circle. If r is the radius of a circle, then the surface area of a circle is 4 pi r square. 4 pi r square. Then the charge q becomes, already dr is there. We have 4 pi r square is there. Then we can write dr is equal to, it is q by 4 pi r square. 4 pi r square. Or in general, we can write d is equal to, it is q by 4 pi r square into AR, where AR is a unit vector. So the same electric flux density we can find out by using the ordinary expressions. Or if you find out the electric field density, E is equal to, we have Q by, it is 4 by epsilon naught R square into AR. So we can find out by using the derivation, or simply by applying Gauss law, we can find out the electric field density and electric flux density for a Gaussian surface or for a point charge. So this is about the application of Gauss law to the point charge. Next, we'll apply the Gauss law to an infinite line charge. An infinite line charge. So let us assume a line charge, an infinite line charge of uniform charge rho L coulombs per meter, which is lies along the z-axis. Or along the z-axis, you assume assume a line charge. Assume a infinite line charge. Infinite line charge. So here, then after assuming the line charge, we need to apply a Gauss law. To apply a Gauss law, we need to follow the rules and regulations. The first rule is, we need to check that whether there is some uniform charge distribution is there or not. So for that uniform charge distribution, here I am assuming a cylinder or cylindrical surface along the along the infinite line. Along the infinite line, let us assume a cylindrical surface. So because of the cylindrical surface, there exists a uniform charge distribution. Uniform charge distribution or symmetrical charge distribution. So when symmetrical charge distribution is there, then we need to construct a mathematical circle. So here the mathematical circle is cylindrical surface. Then the third one is we need to check that the electric flux density D is tangential or normal to the surface. Here at any point on a surface, except this top and bottom, at any point on the cylindrical surface, D should be normal to the that cylindrical surface. When D is normal, we can write D is equal to D rho into A rho. We can apply the Gauss law to the cylindrical surface. If you apply Gauss law to a cylindrical surface, where it is rho L is equal to charge Q, according to Gauss law, it is surface integral D into ds, which is nothing but in place of D, you substitute D rho into A rho, where A rho is the unit vector. Therefore, D rho into surface integral 1 into ds, which is equal to D rho into, here the surface area of a cylinder is 2 pi rho L, where rho is the radius of cylinder, L is the length of the cylinder, where rho is the radius, L is the length of the cylinder. Then the surface area of a cylinder is 2 pi rho L. Then here we can write rho L is equal to it is D rho into 2 pi rho L. D rho into, it is D rho into 2 pi rho L. Or we can write D rho is equal to, it is rho L by 2 pi rho L. Or in general, we can write D is equal to, it is rho L by 2 pi rho L into, or here it is length is small, you can assume that length L is small, it is A rho. So it is a electric flux density due to the line charge. If it is electric field density, we can write E is equal to, it is rho L by 2 pi epsilon naught rho L into A rho. Or if you multiply epsilon naught and E, it is D is equal to epsilon naught E, which is nothing but rho L by 2 pi rho into L into A rho. So this is about the electric flux density of a line charge, infinite line charge, when we apply a Gauss law. So in this way, we can apply Gauss law to the surface, infinite sheet of charge, or we can apply the volume charge also. So here we know that Gauss law states that, let us assume a closed surface. In any closed surface, the flux in any closed surface psi is equal to the charge enclosed in the closed surface. So according to Gauss law, the flux in any closed surface psi is equal to the charge enclosed in the closed surface. So we'll apply the same Gauss law to a point charge, line charge, surface charge, and volume charge. In previous video, already we have discussed the application of Gauss law to point charge and line charge. Now we are going to discuss the application of Gauss law to sheet charge or surface charge. So let us assume an infinite sheet of uniform charge. With the charge density rho s coulombs per meter square lying on the z equal to 0 plane. So assume an infinite sheet. To apply a Gauss law, here we need to follow some rules and regulations. So here the first one is, to apply a Gauss law, we need to check that whether there is some uniform charge distribution is there or not. If there is some uniform charge distribution, then only we can apply the Gauss law. Let us assume there is some uniform charge distribution. If uniform charge distribution is there, next one is we need to construct a Gaussian surface or Gaussian circle. So here let us assume, I am assuming a rectangular box along the surface, infinite sheet. It is an infinite sheet. Along the infinite sheet, I am assuming uniform charge distribution. If there is some uniform charge distribution, next step I am going to construct a Gaussian surface. Let us assume the Gaussian surface is a rectangular box. So here when we place the rectangular box along a infinite sheet charge, the sheet will cut the rectangular box into two parts. The two parts are parallel to each other. One is the top part and other one is the bottom part. There are two parts, top part and bottom part. So next, third one is we need to check that the electric flux density D is normal to the surface or tangential to the surface. If D is normal to the surface, then only we can apply the Gauss law. Next, let us assume D here at point B, we need to find out the, here at point B, we need to find out the electric field intensity. Here at point B, the electric flux density. The electric flux density, D is normal to the surface. D is normal to the surface. Therefore, when D is normal to the surface, here we can assume D is equal to dz into az, where dz is the electric flux density along the z direction, az is unit vector along the z direction. Next. So if you apply Gauss law to the infinite sheet charge, we know that already we know the charge. We know that the charge in that particular, in the infinite sheet is, it is rho s into, it is surface integral ds. Rho s, where rho s is the surface area of a infinite sheet and it is surface integral into ds. Next, which is according to the Gauss law, the flux is equal to the charge enclosed. The flux psi is equal to charge enclosed. So here, if you assume the charge is rho s into surface integral ds, then the charge can be assumed as, or we can define the charge for a in surface charges. It is q is equal to, it is surface integral d into ds. It is a charge in a surface area or surface charge. So here, according to the Gauss law, the total flux psi is equal to charge enclosed in the surface, closed surface. Therefore, here we can write rho s into surface integral ds is equal to, which is nothing but charge, which is equal to, it is surface integral d into ds. Surface integral d into ds. So here we can assume it is rho s into, it is surface integral 1 into ds. If you assume the surface area of a, that the infinite sheet is A, then it will be rho s into A, which is equal to, on right hand side, it is surface integral d into ds is there. We can substitute d is equal to dz into az. Therefore, surface integral dz into az, or it can be expressed as surface integral, it is dz into, or we can express the surface integral as, it is dz into, it is integral top part ds plus integral bottom part of that total area. So here, if you we can observe the circuit diagram also. If you observe the circuit diagram, in circuit diagram, the infinite sheet will cut the total rectangular box into two parts, top part and bottom part. Here we need to assume the two areas. Top area is A and bottom area is A, like that, because both the areas are similar. Therefore, we can express it as, it is rho s A is equal to, it is dz into top area is A, bottom area is A. Therefore, it is ds is equal to, we can write dz or ds. ds is equal to, it is rho s by 2 into az. Rho s by 2 into az. So this is the electric flux density of an infinite sheet. So from this we can find out the electric field intensity, because we know that electric flux density D is equal to E into epsilon naught. Therefore the electric field intensity E is equal to D by epsilon naught, which is equal to rho s by 2 epsilon naught into Az, where Az is the unit vector along the z direction. So this is about the application of Gauss law to infinite sheet charge. So if you apply Gauss law to infinite sheet charge, within 3-4 steps we can find out the electric flux density. Next. So next one is uniformly charged sphere. So here we are applying the the Gauss law to uniform volume charge. So here to apply a Gauss law to volume charge, let us consider a sphere of radius A. Let us assume a sphere of radius A with a uniform charge density rho naught coulombs per meter cube. Then to determine electric flux density D at every point, we need to construct a Gaussian surface. First, we need to check that whether there is some uniform charge distribution is there or not. If uniform, let us assume uniform charge distribution is there. When uniform charge distribution is there, we need to construct a Gaussian surface or Gaussian circle. So here we are assuming a sphere of radius A, because we are assuming a sphere of radius A, we can construct the Gaussian surface inside the sphere and outside the sphere. You can construct the Gaussian surface or Gaussian circle inside the sphere and outside the sphere. So therefore, there are two types of Gaussian surfaces here. Therefore, here the radius where r is the radius of, let us assume r is the radius of Gaussian circle. Then r is less than or equal to a, and r is greater than or equal to a. First case is the r is less than or equal to a, and in second case r is greater than or equal to a, where a is the radius of actual sphere. We need to find out the we need to apply the Gauss law to these two conditions. First one is r is less than or equal to a, and second condition is r is greater than or equal to a. And we need to find out the two electric flux densities. We need to find out the two electric flux densities. First condition. So here r is less than or equal to a. When r is less than or equal to a, the total charge enclosed by the spherical surface of radius r is, the total charge enclosed by the spherical surface of radius r is. Already we know that for volume charge, the charge enclosed equal to, or the charge equal to, it is volume integral q is equal to, volume integral rho v dv. Q is equal to volume integral rho v dv. Or in other way we can write q is equal to, it is rho v into volume integral 1 into dv. Here we assume that the volume integral rho v is equal to rho naught. Therefore, q is equal to rho naught into volume integral 1 into dv. We know that the volume of the sphere is, it is 4/3 pi r cube. 4/3 pi r cube, where r is the radius of Gaussian sphere. Therefore, the charge enclosed q is equal to, or q enclosed equal to, here we can write rho naught into 4/3 pi r cube. 4/3 pi r cube. Next, similarly, we will find out the flux in the surface area. The flux can be expressed as, the flux psi is equal to, it is surface integral d into ds. We know the formula. The flux in any closed surface psi is equal to, it is surface integral d into ds. Because d is normal at any, d is the normal at any point on the sphere, we can assume d is equal to dr into ar. We can assume d is equal to dr into ar. Therefore, in place of d, we can write dr here. Therefore, psi is equal to, it is surface integral dr into ds. Or it is dr into surface integral 1 into ds. Psi is equal to surface integral dr into surface integral 1 into ds. We know that the surface area of a sphere is 4 pi r square. The surface area of the volume of a sphere is 4/3 pi r cube. The surface area of a sphere is 4 pi r square. Therefore, we can write psi is equal to, it is dr into 4 pi r square. And in simple, d is equal to, we can write d is equal to, psi is equal to dr 4 pi r square. Here, according to Gauss law, we need to equate the charge enclosed equal to flux in a closed surface area. Therefore, if we equate the q is equal to psi, then here we have 4/3, it is rho naught into 4/3 pi r cube is equal to dr into 4 pi r square. R square cancel each other. Here 4 pi cancel each other. Then we can write dr is equal to, it is rho naught by 3 into r into, it is ar. dr is equal to, the electric flux density d is equal to rho naught by 3 into r into ar, where ar is the unit vector. So this is for 0 less than or equal to r less than or equal to a, when the radius of Gaussian sphere is less than the radius of actual sphere. Next, second condition is, when we assume the radius of Gaussian surface r is greater than or equal to radius of the sphere a, then again we need to find out the charge enclosed. So in a similar fashion, the charge enclosed q enclosed equal to, we need to have, it is volume integral rho v into dv. Already we assume that rho v is equal to rho naught. It is rho naught into volume integral 1 into dv. We know that the volume of a sphere is 4/3 pi r cube actually. 4/3 pi r cube. Therefore, it is rho naught into 4/3 pi a cube. Here why it is A means, so if you observe the circuit diagram. So here second, if you observe the second circuit diagram, here A is the, let us assume it is the A is the radius of a actual sphere and R is the radius of Gaussian sphere. Here radius of Gaussian sphere is greater than the radius of actual sphere and it is outside the sphere. So when Gaussian sphere is outside the sphere, we need to consider the actual radius of the sphere only. Therefore, the actual radius of the sphere is A. Therefore, the volume of the sphere is, it is rho naught into 4/3 pi A cube in place of pi R cube, 4/3 pi R cube. We need to consider the actual radius. Therefore, rho naught into 4/3 pi A cube. Similarly, we need to find out the flux enclosed in a surface. Here the flux enclosed in a surface is psi is equal to, the flux enclosed in the surface, psi is equal to, we have equation, psi is equal to, we have equation, surface integral d into ds. Therefore, d is normal at everywhere. Therefore, we can assume d equal to dr into ar, dr into this surface integral 1 into ds. The surface area of a sphere is, it is 4 pi r square. The surface area of a sphere is 4 pi r square. Therefore, dr into 4 pi r square. Now equate the flux equal to the charge enclosed. The flux in a closed surface is equal to the charge enclosed in that closed surface. Therefore, psi is equal to q. When psi is equal to q, it is dr into 4 pi r square equal to rho naught into 4/3 pi a cube. And 4 pi cancel each other. Then dr is equal to, we can write dr equal to, it is rho naught into a cube by it is 3r square into ar. Or simply we can assume, or we can write d electric flux density, d is equal to, it is rho naught a cube by 3r square into ar, where ar is the unit vector along the r direction. Unit vector along the r direction. So this is about the application of Gauss law to point charge, line charge, surface charge and volume charge. So by applying the Gauss law in a simple manner, we can derive the electric flux density and electric field intensity. So here from this equation, from D we can find out the electric field intensity also. Electric field intensity, here E is equal to, we can write D by epsilon naught. Therefore, the electric flux density D is equal to, here it is rho naught into a cube by 3 epsilon naught r square into ar. So in this way we can find out the both electric field intensity and electric flux density by applying Gauss law to all the charge densities: point charge, line charge, volume charge and surface charges. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.